Okay, this is a recap over the first half of Unit 1 that we did in class. So this is Unit 1.1 to 1.5. So I'm just going to record what we did in class. That way you can go back and look at the video, as well as finding the more detailed PDF with the diagrams on Schoology. So 1.1, what can we learn from data? So remember, we learned two types of data. We learned about quantitative data, okay? And then we also learned about categorical data. Remember, quantitative data is anything that can be assigned a numerical value. So think average. When they ask you to find the average of a distribution, then you know they're talking about quantitative data, because we can only take the average if we have data that is a numerical value. Examples of that could be the average number of limes bought at H-E-B at a day. Another example of that could be the average of exam scores. So I give the example here that says if we take these exam scores, 80 plus 90 plus 70 plus 85 plus 75, divide it by the total number of exam scores, we get 80 as the average. We also learned that there was two different types of quantitative data. First, we have discrete, then we have continuous. So discrete data, think whole numbers. Continuous data, think decimals within intervals. Okay, so not just decimals itself. Okay, because a special case of discrete data would be shoe size. Okay, shoe sizes can come in whole numbers, so like a size 6, or it can also come in half sizes, like a 7.5. So even though 7.5 is a decimal, it's not a continuous decimal within an interval. So that means if it is something that is possible, like countable, so when we're thinking of shoe sizes, we think 7, 7.5, 8, 8.5, so on and so forth, it's still considered discrete. Because we could not have a 7.5.267 shoe size. It's not that specific within an interval of numbers. Some examples of this is age, because age is a number, income, and blood pressure. For categorical data, that is everything that can be grouped in a category. So I want you to think proportion or percentage. So if they're asking you to find the proportion or the percentage of a distribution, you know that this is categorical data where everything is in categories. Okay? And we talked a little bit about this when we did the favorite classes lab, when we were comparing to see if our core classes could reflect our favorite elective classes. Okay, and classes were all in different categories like sciences, maths, English, so on and so forth. Other examples of that could be eye color. Okay, so we have brown, green, blue, so on and so forth. Another example could be dog breeds. Okay, when we talk about dog breeds, we don't go say that's breed number 1, breed number 2, breed number 3. No, we describe the different breeds. So there's Chihuahuas, Dachshunds, so on and so forth. One important thing about statistics is to always mention the context of data. So context of data means that we are going to describe the problem with our answers. So if you think back to a normal math class, and we're using the examples of limes purchased at H-E-B, if you were to just solve the whole thing and get L is equal to 5, this would be okay for any other math class. But statistics, think of it like the English of math. So anytime we have to answer a question, we have to answer it in a complete sentence using the context of what the problem is about. So instead of saying L is equal to 5, we would say the average number of limes purchased at H-E-B is 5. We'd have to write that whole thing. Okay, we also learned how to describe data. So when we describe data, we use the acronym SOCV, where S is shape, O is outlier, C is center, and V is variability. So when we're talking about the shape, we're talking about the appearance of the diagram. So whether that diagram or graph is symmetric or if it's skewed to the left or to the right. Then we describe the outlier. So remember, the outlier are the extreme values, okay? Even if there is not an outlier, you still need to write that sentence. This diagram doesn't show any outliers, okay? Then we have the center. The center is where you would describe the median or the mean, depending on what type of diagram you're looking at. And then lastly, we would describe the variability. Variability is the range, so how far apart the values are from each other. So when we're describing data, think of each of these as a sentence, okay? So you should have at least 4 sentences describing that data, and within those sentences, you are describing the shape, the outlier, the center, the variability, and then within all of that, you're including your context, so what the problem is about. Okay, in this course, we're going to talk about 2 different types of statistics. We're going to talk about descriptive, so that's what we've been doing so far, and then inferential stats. So descriptive is where we, as the individual, are collecting, organizing, summarizing, and presenting the data ourselves. Inferential stats is where we are using other people's data or old data to make predictions. When we are describing data or looking at data, it is always best to understand the who, what, when, where, why, and how of data. So the who of data is what the data is, who the data is being collected of. So it could be an individual who is a part of a experiment, and we are collecting data from that individual. Or it could be data that we are collecting from, let's say, animals, the environment, or inanimate objects. The what of data we describe as the variable. So the what is what we're looking at, what we're comparing and contrasting. So like in any other math, there are 2 types of variables. We have the dependent variable, and that's the variable that is being measured. And then the independent variable, and that's the variable that's being manipulated. But if you think back to a science class, when you are comparing these variables, you always have another variable, and that is the controlled variable, so the constant. This is the variable that does not change, okay? And just like in any other math, if we have a dependent value, that dependent value is always going to depend on the independent value. Then we have the when and the where. So the when is when the data is being collected. So think time period. So we could have data that is collected in the 1800s versus data that is collected now in 2024. If we know that these 2 sets of data are collected in different time periods, we couldn't always compare them or put them under the same predictions based on what was happening during the time period. The where is where was the data collected. So let's say we had data collected in the United States and then we had data collected in Germany. We couldn't necessarily compare that data because we have a lot of different factors that play in, and one of those factors is location and culture. The why is the most important. The why of data is the question we ask in order to make a prediction between the relationship of the variables. How is how the data is collected. So I want you to think like if you were to give a survey or if you were to just go and make an observation and collect data on your own. So it's how the data is collected. Okay, 1.2, the language of variation. Variables can be measured at different levels. So we have the first level, which is the interval level, and that is a measurement scale. So a scale that includes an interval. So let's say we're measuring from 5 minutes to 8 minutes. Then we have a nominal level, which is the lowest measurement, an ordinal level, which is where our variables are ranked based on their order, and then a ratio level is similar to an interval level, so we're still going to have a set interval, but with a ratio, there is a true zero value. Because if we were to take the proportion, let's say 0 over 5, that would give us a true value of 0. Then we went through this example, and on this example, we were comparing industries with the number of injuries that the employees in that industry reported. So we had two variables here. We had the industry, and then we had the number of injuries. The industry is based in categories, so this data is categorical. The number of injuries are numbers, so this data is quantitative. And not only is it quantitative, it's quantitative discrete because we are looking at whole numbers. If we were to look at this table and make a prediction off of the table, one prediction we could make is like, hey, it's safer to work at a railroad because it has fewer injuries. However, that prediction would only be true if we didn't have any other data based off this. But let's say we had data of the number of employees employed within each industry. So if we had compared, let's say, railroad to airline, airline looks like they have a lot of injuries, but I bet you a whole lot more employees work for airlines than they do railroads. Okay, railroad is just not a popular mode of transportation anymore compared to airlines. So it makes sense that airlines has the highest number of injuries because they probably have the highest number of employment. 1.3, representing categorical variables with tables. So in this section, we learned about two different tables. The first table was a frequency table, and then the next table was a relative frequency table. So a frequency table is where the data is listed in one column in categories, and then in the other column is the number of elements within that category. So for example, if we had the data set listed below, 2, 3, 3, 5, 5, 5, 7, 7, 9, we could take each of these data points and write them one time to represent our value. So I have 2, 3, 5, 7, 9. Then to find the frequency, I'm seeing how many times this number appears. So number 2 appears one time. Number 3 appears 2 times. Number 5 appears 3 times. Number 7 appears 2 times. And number 9 appears 1 time. So this table right here would just be our frequency table. But if we were to add another column and call that column the relative frequency, remember relative frequency shows the percentage of the elements within the total set of data. So we would take the frequency and divide it by the total. So there's 9 numbers here. So I would take 1 divided by 9, and that would give me 11%. And I would do the same for each of these numbers here, and I would get 22%, 33%, 22%, and 11%. And notice if we were to add all those percentages together, we would get very close, if not exact, 100%, because that 100% is telling us that we used the entire data that was in that data set. 1.4 is representing categorical with graphs. So we talked about 2 graphs in class, and that was the bar graph and the pie chart. A bar graph displays frequencies or relative frequencies, and a pie chart is a graph divided into slices for each category. Okay. One thing that we didn't mention is a contingency table, and a contingency table is used to analyze categorical data and help us understand the patterns in the data. So that's the important keyword there. And then lastly, 1.5, representing quantitative data with graphs. We talked about a couple of these, and the first one was a histogram. So a histogram divides data into bins. So remember when we draw a histogram, it looks like a bar graph. So we draw a bunch of bars next to each other, but those bars don't represent a single point of data. They represent an interval of data. They call that interval of data a bin. Each bin represents intervals of data. One that we didn't get to talk about was frequency polygons. And frequency polygons display the distribution by using lines to connect the midpoints of each bin. So in order to create a frequency polygon, we need a histogram. And once we have the histogram, we find the midpoints of each of those intervals and then connect it to create a trend line. Then we have Ogilvie's graph, which is a frequency plot that represents cumulative distribution. So this one's a good one if we want to look at the entire set of data. Stem plots are similar to histograms, but preserve individual data. So on histograms, you're not able to pinpoint one individual data point, except only the interval of that data point. With stem plots, just like dot plots, we were able to see each individual data point that is plotted there. Stem plots, we see that in numbers, and dot plots, we see that in dots. And remember, on Schoology, I have a more detailed version of these notes that have an example diagram of each of these if you want to go ahead and check that out.